Picture this: a grain so hardy it can survive months without rain, so nutritious it outperforms quinoa, and so ancient that our ancestors were cultivating it 10,000 years ago. Yet somehow, this wonder crop nearly disappeared from dinner tables across the globe. Now, as climate change reshapes agriculture and consumers demand healthier foods, millets are staging one of the most remarkable comebacks in farming history. While most Americans have never heard of finger millet, pearl millet, or foxtail millet, these small but mighty grains are quietly revolutionizing agriculture from the drought-stricken fields of Arizona to the vertical farms of Brooklyn. In 2023, global millet production reached over 28 million tons, with demand growing at 4.5% annually. That's faster growth than any other cereal crop, including the trendy ancient grains that have dominated health food stores for the past decade. What makes this comeback so fascinating isn't just the numbers. It's the story of how a group of forgotten crops, once dismissed as poor man's food, are now being hailed as the future of sustainable agriculture. From NASA researchers studying millet cultivation for Mars missions to Silicon Valley entrepreneurs launching millet-based startups, this ancient grain is capturing attention in the most unexpected places. The millet renaissance represents something bigger than just another superfood trend. It's a glimpse into how agriculture might adapt to our changing world, where water scarcity, extreme weather, and growing populations demand crops that can do more with less. As we'll discover, millets don't just survive harsh conditions, they thrive in them, offering farmers a path toward resilience that industrial agriculture has struggled to provide. The story of millets is ultimately the story of agricultural innovation coming full circle. In an era where high-tech solutions often dominate farming headlines, sometimes the most revolutionary approach is to look backward, to rediscover the wisdom embedded in crops that have sustained civilizations for millennia. This is that story. Today, millet cultivation spans every continent except Antarctica, with India and China leading production, but exciting developments happening right here in American farm fields. From the Great Plains to the Southeast, forward-thinking farmers are experimenting with these climate-smart crops, finding that what's old can indeed become new again. The global millet industry now represents over $2.8 billion in annual value. But more importantly, it represents hope. Hope for smallholder farmers facing unpredictable weather. Hope for consumers seeking nutritious alternatives to processed foods. And hope for a planet that needs agriculture to become more sustainable, not just more productive. Understanding how millets work, from seed to supermarket, reveals why this ancient grain family is positioned to play a crucial role in feeding the world's growing population. It's a journey that takes us through cutting-edge breeding programs, innovative processing techniques, and supply chains that are being rebuilt from the ground up. The transformation of millets from subsistence crops to premium health foods didn't happen overnight. It required decades of research, investment, and most importantly, a shift in how we think about what makes a crop valuable. Size isn't everything. Sometimes the smallest grains carry the biggest potential. Let's dive into this remarkable world where ancient wisdom meets modern innovation, where traditional farming practices are being enhanced by precision agriculture, and where a grain the size of a mustard seed is helping to reshape the future of food. Millets aren't just one crop, but an entire family of small-seeded grasses that have adapted to some of the world's harshest growing conditions. Unlike corn, wheat, or rice, which require specific climates and abundant water, millets represent nature's answer to agricultural resilience. The major species include pearl millet, which dominates arid regions of Africa and India, finger millet, prized for its nutritional density and storage properties, foxtail millet, known for its quick maturity, and proso millet, which has found a niche in the American Great Plains. What sets millets apart in today's agricultural landscape isn't just their drought tolerance, though that's certainly impressive. These crops can produce viable yields with as little as 200 millimeters of annual rainfall, compared to the 500 to 800 millimeters that wheat typically requires. More importantly, millets offer something that modern agriculture desperately needs: stability in an unstable climate. The global millet market has undergone a dramatic transformation over the past decade. What was once primarily grown for subsistence or animal feed now commands premium prices in health food stores from Los Angeles to London. The United States, despite being a relatively small producer, has emerged as a significant player in the high-value millet market, with production concentrated in Colorado, Nebraska, and the Dakotas. This shift reflects changing consumer preferences, but it also represents a fundamental rethinking of agricultural priorities. In an era where sustainability matters as much as productivity, millets offer a compelling value proposition. They require fewer inputs, tolerate marginal soils, and can fit into crop rotation systems that improve overall farm health. The economic impact extends beyond farm gates. Processing facilities that were once focused on corn and soy are retooling to handle millets. New supply chains are emerging to connect small-scale producers with specialty food manufacturers. Investment in millet research and development has increased by over 300% since 2020, driven by both government initiatives and private sector interest. Traditional millet farming relied heavily on indigenous knowledge and local varieties adapted to specific microclimates. Farmers would select seeds from their best-performing plants, gradually improving their crops over generations. This approach created incredible genetic diversity, with some regions maintaining dozens of distinct millet varieties, each with unique characteristics suited to local conditions. Modern millet production builds on this foundation while incorporating scientific breeding methods and technological tools. Today's millet farmers use weather monitoring systems, soil sensors, and GPS-guided equipment alongside traditional techniques like companion planting and natural pest management. The result is a farming system that combines the resilience of ancient practices with the precision of modern agriculture. The contrast between traditional and contemporary millet farming is striking. Where once farmers might plant by lunar cycles and harvest by hand, modern operations use precision seeders and combine harvesters. Yet the fundamental characteristics that made millets valuable to ancient civilizations, drought tolerance, pest resistance, and nutritional density, remain as relevant today as they were thousands of years ago. Market forces are driving this evolution. As demand for gluten-free, high-protein grains increases, millet prices have reached levels that make commercial production economically attractive. Premium organic millets can command prices of over $2,000 per ton, compared to around $200 for conventional corn. This price differential is creating opportunities for farmers willing to learn new techniques and adapt to specialized markets. The industrialization of millet production has also brought challenges. Mechanization designed for larger grains doesn't always work well with millet's small seeds. Storage and handling require different approaches. Quality standards developed for wheat or rice don't necessarily apply to millets. These challenges are spurring innovation in agricultural equipment and post-harvest technology. International trade in millets has expanded dramatically, with exports growing by over 80% in the past 5 years. India remains the dominant exporter, but countries like Sudan, Niger, and surprisingly, the United States are becoming significant players in specialty millet markets. This global trade network is creating new opportunities for farmers while also establishing quality standards and traceability systems that didn't exist in traditional millet production. The breeding and selection process for modern millet varieties represents a fascinating blend of ancient wisdom and cutting-edge science. Unlike hybrid corn or genetically modified soybeans, most commercial millet varieties are still open-pollinated, meaning farmers can save seeds from their harvest for the next season. This characteristic has preserved genetic diversity while allowing for continuous improvement through selective breeding. Contemporary millet breeding programs focus on traits that matter to both farmers and consumers. researchers are developing varieties with higher yields, more uniform ripening, and improved nutritional profiles. Some programs are working on millets with enhanced protein content, while others focus on developing varieties that can thrive in specific climatic conditions or resist particular pests. The breeding process typically begins with the collection and evaluation of genetic material from traditional varieties and wild relatives. Plant breeders maintain seed banks containing thousands of different millet accessions, each with unique characteristics. These genetic resources serve as the foundation for developing new varieties that combine desirable traits from multiple sources. Crossing different millet varieties requires patience and precision. Unlike some crops that can be hybridized in greenhouse conditions, millet breeding often takes place in field environments that closely mimic the conditions where the final varieties will be grown. This approach ensures that new varieties will perform well in real-world farming situations. The evaluation process for new millet varieties is comprehensive and time-consuming. Potential varieties are tested across multiple locations and growing seasons to assess their performance under different conditions. Researchers evaluate everything from germination rates and growth patterns to nutritional content and cooking quality. Modern breeding techniques are accelerating this traditionally slow process. Marker-assisted selection allows breeders to identify desirable traits at the genetic level without waiting for plants to mature. Genomic selection uses comprehensive genetic profiles to predict how different varieties will perform, enabling more efficient breeding decisions. The seed production system for millets is becoming increasingly sophisticated. Foundation seed is produced under carefully controlled conditions to ensure genetic purity and high quality. This seed is then multiplied through a series of steps, with each generation subjected to rigorous quality control measures. Certification programs for millet seed ensure that farmers receive varieties that meet specific standards for purity, germination, and freedom from diseases. These programs are particularly important for organic producers who require certified organic seed to maintain their certification status. The timing of millet breeding programs is crucial because of the crop's relatively short growing season. Most millet varieties mature in 60 to 90 days, which allows for multiple breeding cycles per year in favorable climates. This rapid generation time is an advantage for breeders working to develop new varieties quickly. Storage and handling of millet breeding material requires special attention because of the small seed size. Genetic material is typically stored in climate-controlled facilities with precise temperature and humidity controls. Some breeding programs maintain duplicate collections in different locations to protect against loss of valuable genetic resources. The global network of millet researchers and breeders shares genetic material and breeding techniques through international organizations. This collaboration accelerates the development of new varieties and ensures that improvements benefit farmers worldwide. Many of the millet varieties now grown in the United States originated from breeding programs in India, Africa, or other millet-producing regions. Growing millets successfully requires understanding their unique characteristics and adapting farming practices accordingly. Unlike crops that demand specific soil types or precise nutrient management, millets are remarkably adaptable. But this adaptability comes with its own set of considerations for optimal production. The growing season for millets varies by species and location, but most varieties are planted in late spring or early summer when soil temperatures reach 60 to 65 degrees Fahrenheit. This timing is critical because millet seeds are small and vulnerable to cool, wet conditions that can cause poor germination or seedling diseases. Soil preparation for millets is generally less intensive than for other grains. Most millet species prefer well-drained soils, but can tolerate a wide range of soil types, from sandy loam to clay. The key is ensuring good drainage, as millets are susceptible to waterlogged conditions despite their reputation for drought tolerance. Planting techniques for millets have evolved significantly with mechanization. Traditional broadcasting methods are still used in some regions, but precision planting with specialized equipment is becoming more common in commercial operations. The small seed size requires careful calibration of planting equipment to achieve proper seeding rates and depth. Nutrient management for millets is typically straightforward compared to other grains. Most varieties require moderate levels of nitrogen, phosphorus, and potassium, but they're generally more efficient at utilizing available nutrients than corn or wheat. This efficiency is part of what makes millets attractive for sustainable farming systems. Water management represents one of the most significant advantages of millet production. While these crops can survive with minimal rainfall, they respond positively to adequate moisture during critical growth periods. The key is providing water during germination and early growth, then allowing plants to use their natural drought tolerance during later stages. Pest and disease management in millet production benefits from the crop's natural resistance to many problems that affect other grains. However, specific pests like stem borers and diseases like downy mildew can cause significant losses if not properly managed. Integrated pest management approaches that combine resistant varieties, cultural practices, and targeted treatments are most effective. The growth stages of millets are distinct and require different management approaches. The establishment phase, from planting to the four-leaf stage, is when plants are most vulnerable to environmental stresses. During this period, adequate moisture and protection from weeds are crucial for successful establishment. Tillering, the process where plants develop multiple stems from a single root system, is a critical phase that determines final plant density and yield potential. Proper nutrition and moisture during tillering can significantly impact the number of productive stems each plant develops. The reproductive phase, from flowering to grain filling, is when proper nutrient and water management has the greatest impact on final yields. Most millet varieties are sensitive to stress during this period, and adequate nutrition is essential for proper grain development. Monitoring plant health throughout the growing season involves regular scouting for pests, diseases, and nutrient deficiencies. Modern millet farmers use various tools, from simple visual inspections to sophisticated remote sensing technologies, to track crop development and identify potential problems early. Environmental factors play a crucial role in millet production success. Temperature extremes, either too hot or too cold, can impact germination and plant development. Wind protection may be necessary in exposed locations, as millet plants can be prone to lodging under severe conditions. Weed management in millet production requires careful attention because millet seedlings are small and can be easily overwhelmed by competitive weeds. Pre-emergence herbicides in cultivation are commonly used, but the timing and selection of weed control methods must be carefully matched to the specific millet variety and growing conditions. The harvest timing for millets is critical because the small grains can shatter easily if left too long in the field. Most varieties are ready for harvest when the grain moisture content reaches 20 to 25%, though this can vary depending on intended use and storage facilities. Before harvest, millet crops undergo several important preparation steps that ensure optimal quality and yield. The pre-harvest period, typically the final 2 to 3 weeks before cutting, is crucial for determining the final grain quality, protein content, and overall nutritional value of the crop. Crop monitoring during the pre-harvest phase involves regular assessment of grain moisture content, which directly impacts harvest timing and post-harvest handling requirements. Farmers use portable moisture meters to track moisture levels, aiming for the optimal harvest window when grains have reached physiological maturity but retain enough moisture for safe handling. Field scouting intensifies during this period, with particular attention to identifying areas of the field that may be maturing unevenly. Millet varieties can show significant variation in maturity even within a single field, requiring farmers to make decisions about whether to harvest the entire field at once or conduct multiple harvests to optimize quality. Weather monitoring becomes critical during the pre-harvest period because unexpected rain can significantly impact grain quality and increase harvest losses. mature millet grains are susceptible to shattering, and wet conditions can cause sprouting in the head, which reduces grain quality and market value. Pre-harvest treatments may include desiccation in some commercial operations, though this practice is less common with millets than with other grains. When used, desiccants help ensure uniform moisture content across the field and can reduce the risk of weather-related harvest losses. Quality assessment during the pre-harvest period involves sampling grains from different areas of the field to evaluate color, size, uniformity, and freedom from disease or pest damage. This assessment helps farmers make informed decisions about harvest timing and marketing strategies. Storage preparation begins well before harvest, with farmers cleaning and inspecting storage facilities to ensure they're ready to receive the new crop. Proper storage is particularly important for millets because the small grain size makes them susceptible to insect infestation and requires different handling approaches than larger grains. Harvest equipment preparation is essential because millet's small grain size and tendency to shatter require specialized settings on combines and other harvest machinery. Farmers typically adjust cylinder speeds, concave clearances, and cleaning systems to minimize grain losses during harvest. Transportation logistics are planned during the pre-harvest period, with arrangements made for moving grain from field to storage or processing facilities. The timing of these arrangements is crucial because millet harvest periods can be relatively short, and delays can result in significant quality losses. Market preparation involves finalizing contracts and arrangements with buyers, whether for direct sales to consumers, processing companies, or export markets. Many millet producers work with specialized marketing cooperatives or brokers who understand the unique characteristics of millet markets. Documentation and traceability systems are established during the pre-harvest period to meet the requirements of organic certification, food safety programs, or specialty market demands. These systems track everything from seed sources and production practices to harvest dates and storage conditions. The primary processing of millets begins immediately after harvest and represents a critical transformation from raw agricultural product to food ingredient. Unlike wheat or corn, which have well-established processing infrastructures, millet processing requires specialized equipment and techniques that accommodate the unique characteristics of these small grains. Initial cleaning is the first step in millet processing and involves removing foreign materials like stones, chaff, and other crop residues. This process is more challenging with millets than with larger grains because the size differential between millet grains and contaminants is often minimal. Specialized cleaning equipment uses air currents, sieves, and gravity separation to achieve the high purity levels required for food applications. Dehulling, the removal of the outer grain coat, is a crucial step that significantly impacts the final product's nutritional value and cooking characteristics. Traditional dehulling methods use stone mills or mortars, but modern commercial processing employs specialized dehulling machines that use controlled abrasion to remove hulls while minimizing grain breakage. The dehulling process requires careful calibration because overprocessing can remove valuable nutrients along with the hull, while underprocessing leaves inedible material that affects product quality. Modern dehulling systems use size, grading, and aspiration to separate dehulled grains from hull material and broken pieces. Grading and sorting follow dehulling, with processed millets being separated into different size categories and quality grades. This step is important for ensuring consistent cooking characteristics and meeting specific customer requirements. Advanced sorting systems use optical sensors and air jets to remove discolored or damaged grains. Heat treatment is applied to some millet products to improve shelf life and reduce cooking time. This process, which may involve steam treatment or dry heat, must be carefully controlled to avoid damaging the grain's nutritional properties or creating off flavors. Quality control throughout the processing sequence involves regular testing for moisture content, protein levels, and microbiological safety. These tests ensure that processed millets meet food safety standards and customer specifications. Packaging of processed millets requires specialized equipment and materials because the small grain size creates different flow characteristics than larger grains. Packaging systems must prevent segregation of different grain sizes while maintaining product quality during storage and transportation. The yield from millet processing varies significantly depending on the variety and processing methods used. Dehulling typically results in yields of 70 to 85%, with the remainder consisting of hulls and broken material. These byproducts aren't wasted but are often used for animal feed or other applications. Processing facility design for millets incorporates dust control systems because the small grain size creates significant dust during handling and processing. These systems are important for worker safety and product quality, as well as meeting environmental regulations. Batch processing is common in millet processing facilities because of the relatively small volumes compared to major grains like wheat or corn. This approach allows processors to maintain tight quality control and accommodate the diverse requirements of different millet varieties and end uses. Equipment maintenance in millet processing facilities requires special attention because the small, hard grains can cause accelerated wear on processing equipment. Regular inspection and replacement of wear parts is essential for maintaining processing efficiency and product quality. The economics of millet processing are influenced by the higher value of the processed product compared to raw grain, but also by the specialized equipment requirements and typically smaller scale of operations. Processing margins are generally higher than for commodity grains, but so are the technical requirements and quality standards. Secondary processing transforms basic millet products into value-added foods and ingredients that command premium prices in specialty markets. This stage of processing has experienced significant innovation as manufacturers work to create products that meet modern consumer demands for convenient, nutritious, and flavorful foods. Flour production represents one of the most important secondary processing applications for millets. Millet flour requires specialized milling equipment because the small, hard grains behave differently than wheat during grinding. The milling process must be carefully controlled to achieve the proper particle size distribution while avoiding excessive heat that could damage nutritional properties. Millet flour processing involves multiple grinding stages, with each stage using progressively finer screens to achieve the desired particle size. The flour is then sifted to remove any remaining hull fragments or oversized particles. Some processors use stone mills for specialty flours, which produce different textural characteristics than steel roller mills. Flaked millet products are created using specialized flaking equipment that presses cooked millet grains into thin flakes. This process requires precise control of grain, moisture content, and temperature to produce flakes with the desired thickness and texture. Flaked millets are popular for breakfast cereals and baking applications. Popped millet production involves heating millet grains under controlled conditions to cause them to expand and develop a light, crunchy texture. This process is similar to popping corn but requires different time and temperature parameters because of millet's smaller size and different starch structure. Extruded millet products are created using food extrusion technology to produce shaped products like pasta, snacks, and breakfast cereals. The extrusion process involves mixing millet flour with other ingredients, then forcing the mixture through shaped dies under high pressure and temperature. Fermented millet products represent an important category, particularly in traditional food systems. Modern commercial fermentation processes use controlled cultures to produce consistent products with extended shelf life. These products often have enhanced nutritional value and digestibility compared to unfermented millets. Malted millet production involves controlled germination of millet grains to develop enzymes that convert starches to sugars. This process is used to create malt extracts for brewing and baking applications. The malting process must be carefully controlled to achieve the desired enzyme activity levels. Protein concentration from millet involves separating the protein fraction from starch and other components. This process is still being developed commercially but shows promise for creating high-protein ingredients for food and feed applications. Quality control in secondary processing involves testing for nutritional content, functional properties, and sensory characteristics. These tests ensure that processed products meet specifications for intended applications and maintain consistent quality across production runs. Packaging innovations for millet products focus on maintaining product quality while providing convenient formats for consumers. This includes everything from bulk packaging for food service applications to individual serving sizes for retail markets. The development of new millet-based products requires extensive research and development to understand how millet ingredients behave in different food systems. This work involves food scientists, nutritionists, and culinary professionals working together to create products that meet consumer expectations. Regulatory compliance for millet products involves meeting food safety standards, labeling requirements, and organic certification where applicable. These requirements vary by market and application, requiring processors to maintain detailed documentation and quality systems. The distribution and marketing of millet products represents the final link in the chain from farm to consumer, and it's where the true value of the millet renaissance becomes apparent. Unlike commodity grains that move through well-established channels, millet products require specialized distribution networks and marketing approaches that can effectively communicate their unique benefits to target audiences. Supply chain logistics for millet products are more complex than for conventional grains because of the smaller volumes and diverse product formats. Distributors must handle everything from bulk ingredients for food manufacturers to retail packages for health-conscious consumers, each with different storage, handling, and transportation requirements. The retail market for millet products has expanded dramatically, with products now available in mainstream grocery stores alongside specialty health food retailers. This expansion has required significant investment in consumer education and marketing to help shoppers understand how to use millet products and appreciate their benefits. Food service applications for millets are growing as restaurants and institutional food providers look for ways to offer more diverse and nutritious menu options. This market requires products that can perform consistently in commercial kitchen environments while meeting the cost and convenience requirements of food service operations. Export markets for processed millet products are expanding as international demand grows for gluten-free and ancient grain products. The United States has become a significant exporter of specialty millet products, particularly to markets in Europe and Asia, where consumer awareness of millet benefits is high. The pricing structure for millet products reflects their position as premium ingredients rather than commodity foods. While this creates opportunities for higher margins throughout the supply chain, it also requires careful market positioning and value communication to justify premium pricing to consumers. Brand development for millet products involves creating compelling stories that connect with consumer values around health, sustainability, and authenticity. Many successful millet brands emphasize the ancient heritage of these grains while highlighting their modern applications and benefits. Consumer education remains a crucial component of millet marketing because many potential customers are unfamiliar with how to use these products. This education happens through various channels, including cooking demonstrations, recipe development, and partnerships with nutrition professionals. The organic market segment has been particularly important for millet products, with organic millets commanding significant premiums over conventional products. This market requires specialized certification and supply chain management but offers opportunities for farmers and processors willing to meet organic standards. Private label opportunities for millet products are growing as retailers seek to offer unique products under their own brands. This trend requires processors to work closely with retailers to develop products that meet specific market positioning and price point requirements. The global nature of millet markets means that prices and availability can be influenced by production conditions and policy changes in major producing countries. This creates both opportunities and challenges for processors and marketers who must navigate international market dynamics. Quality assurance throughout the distribution chain ensures that millet products maintain their nutritional value and sensory characteristics from processing facility to consumer. This requires careful attention to storage conditions, handling procedures, and shelf life management. The transformation of millets from subsistence crops to premium food ingredients represents more than just a market trend. It reflects a fundamental shift in how we think about agriculture, nutrition, and sustainability. As we've seen throughout this journey from ancient grains to modern superfoods, millets offer something that our current food system desperately needs: resilience in the face of uncertainty. The millet renaissance is happening at exactly the right time. As climate change makes traditional farming more challenging, as consumers become more conscious of what they eat, and as farmers look for crops that can thrive with fewer inputs, millets provide answers to questions that seemed impossible just a few years ago. What makes this story so compelling isn't just the technical achievements or market success, but the human element. Small-scale farmers finding new opportunities, entrepreneurs building businesses around forgotten grains, and families discovering nutritious foods that connect them to agricultural traditions stretching back millennia. The future of millet production will likely involve even more innovation, from precision agriculture techniques that optimize growing conditions to new processing methods that unlock additional nutritional benefits. But the fundamental appeal of these hardy, nutritious grains will remain constant. As we look toward the next chapter of this agricultural revolution, millets have established themselves as more than just a niche crop. They represent a bridge between ancient wisdom and modern innovation, between traditional farming and sustainable agriculture, between local food systems and global markets. The success of millets opens doors to reconsidering other neglected crops that might offer similar benefits. It demonstrates that sometimes the most revolutionary path forward involves looking backward, to rediscover the potential that was always there, waiting to be recognized and developed. This brings us to another crop that tells a completely different story about global agriculture and international trade. While millets represent the rediscovery of ancient wisdom, our next journey takes us into the world of a fruit that has become so ubiquitous that we often forget the remarkable global network required to bring it to our tables year-round. From the highlands of Ecuador to the ports of Miami, from plantation management to ripening rooms, the banana industry represents one of the most complex and fascinating agricultural systems on Earth. It's a story of international trade, technological innovation, and the challenges of feeding a global population with a single, vulnerable crop. How do billions of bananas make their way from tropical plantations to grocery stores around the world? What does it take to manage a crop that never stops growing, never stops producing, and never stops requiring human intervention? And what happens when an entire industry depends on a fruit that could be wiped out by a single disease? The banana you ate for breakfast this morning traveled further than most people do in a lifetime. It began its journey in a plantation somewhere in Ecuador, Costa Rica, or the Philippines, where it was cut from a tree that isn't actually a tree at all. It was washed, sorted, boxed, and loaded onto a refrigerated ship that maintained a precise temperature of 58 degrees Fahrenheit during a journey that could have lasted 2 weeks. Upon arrival at a North American port, it was transported to a ripening facility where it was exposed to ethylene gas in a carefully controlled environment designed to turn it from green to yellow at exactly the right moment. This intricate dance of timing, temperature, and technology happens 100 billion times each year, making bananas the world's most exported fruit and one of the most traded agricultural commodities on Earth. The global banana trade is worth over $14 billion annually, with Americans alone consuming over 26 pounds of bananas per person each year, more than any other fruit except apples. But here's what makes the banana story truly remarkable. Nearly every banana consumed in the United States is genetically identical. The Cavendish variety that dominates global trade is essentially a clone, propagated not through seeds but through careful cultivation techniques that have remained largely unchanged for decades. This uniformity is both the banana industry's greatest strength and its most dangerous vulnerability. The scale of modern banana production is staggering. A single plantation in Ecuador might cover 5,000 acres and produce 50,000 boxes of bananas every week. These operations employ thousands of workers and require coordination between agronomists, logistics experts, and quality control specialists across multiple countries and time zones. Unlike the millet renaissance we just explored, where ancient crops are finding new markets through innovation and adaptation, the banana industry represents the pinnacle of agricultural standardization and global supply chain management. Every aspect of banana production, from planting to plate, has been optimized for consistency, efficiency, and year-round availability. The banana trade has shaped entire economies, influenced international politics, and created some of the most sophisticated cold chain logistics systems in the world. Countries like Ecuador, Guatemala, and the Philippines have built much of their agricultural infrastructure around banana exports, creating economic dependencies that span generations. Yet this remarkable system faces unprecedented challenges. Climate change is altering growing conditions in traditional banana regions. A fungal disease called Panama disease threatens to devastate Cavendish plantations worldwide, just as it wiped out the previous dominant variety, the Gros Michel, in the 1950s. Labor issues, environmental concerns, and changing consumer preferences are forcing the industry to reconsider practices that have been standard for decades. The banana industry also represents one of the most vertically integrated agricultural systems in the world. Major companies control everything from plantation management to retail distribution, creating efficiencies that allow bananas to be sold for less than $2 per pound in American supermarkets, despite traveling thousands of miles. Understanding how this system works reveals both the possibilities and the perils of modern agriculture. The banana industry has achieved something remarkable, making a tropical fruit available year-round at affordable prices in temperate markets around the world. But this achievement comes with costs that are becoming increasingly apparent as the industry faces new challenges. The environmental impact of banana production extends far beyond the plantations themselves. The energy required to maintain cold chain logistics, the water usage in processing facilities, and the packaging materials needed to protect fruit during transport all contribute to the industry's environmental footprint. Social considerations are equally complex. Banana plantations provide employment for millions of workers in developing countries, but labor conditions and wages have been sources of controversy for decades. Fair trade and organic certification programs have emerged as attempts to address these concerns, but they represent only a small fraction of total banana production. The technological sophistication of banana production often goes unnoticed by consumers who see it as a simple, natural food. In reality, modern banana production involves satellite monitoring of plantations, computerized climate control systems, and logistics networks that rival those of any global industry. As we delve deeper into this world of precision agriculture and global trade, we'll discover how an industry built on a single variety of a single fruit has managed to feed billions of people while creating vulnerabilities that could reshape the entire system. The banana story is ultimately about the trade-offs inherent in modern agriculture. The benefits of specialization and scale versus the risks of uniformity and dependence. The global banana industry operates on a scale that dwarfs most other fruit trades, with annual production exceeding 118 million tons worldwide. This massive output is concentrated in a relatively small number of countries, with Ecuador, the Philippines, Costa Rica, Colombia, and Guatemala accounting for nearly 80% of global banana exports. The industry's geographic concentration creates both efficiencies and vulnerabilities that define its character. Ecuador alone produces over 6 million tons of bananas annually, making it the world's largest exporter with roughly 30% of global market share. The country's banana industry employs over 250,000 people directly and supports an estimated 2 million Ecuadorians when indirect employment is included. This economic significance extends beyond individual livelihoods to national economies, with banana exports generating billions in foreign currency earnings. The transformation of banana production from small-scale farming to industrial agriculture began in the early 20th century when American companies like United Fruit Company, now Chiquita, established large plantations in Central America. This industrialization brought modern agricultural techniques, transportation infrastructure, and processing facilities to regions that had previously engaged in subsistence farming. Today's banana industry is dominated by a handful of multinational corporations that control significant portions of the global supply chain. Companies like Chiquita, Dole, Del Monte, and Fifes manage everything from plantation operations to retail distribution, creating vertically integrated systems that can respond quickly to market demands and maintain quality standards across vast distances. The economic model of banana production relies heavily on economies of scale and standardization. Large plantations can justify investments in specialized equipment, processing facilities, and transportation infrastructure that would be impossible for smaller operations. This scale advantage has led to increasing consolidation in the industry, with large companies either owning plantations directly or contracting with growers who meet strict quality and volume requirements. Modern banana production differs dramatically from traditional methods in both scale and technique. Traditional banana cultivation involves small plots with diverse varieties grown primarily for local consumption. Modern commercial production focuses exclusively on the Cavendish variety, grown in monoculture plantations that can cover thousands of acres. The shift to industrial production has brought significant improvements in productivity and consistency. Modern plantations can produce up to 40 tons of bananas per hectare annually, compared to 10 to 15 tons typical of traditional methods. This increased productivity comes from optimized plant spacing, improved nutrition management, and sophisticated pest control programs. Technology integration in banana production includes satellite monitoring systems that track weather patterns, soil conditions, and plant health across entire plantations. GPS-guided equipment ensures precise application of fertilizers and pesticides, while automated irrigation systems deliver water exactly when and where it's needed. The standardization of banana production extends to every aspect of the operation. Plant spacing, pruning techniques, harvesting procedures, and post-harvest handling all follow strict protocols designed to ensure consistent quality and maximize efficiency. This standardization allows companies to maintain quality standards across plantations in different countries and climates. Export market dynamics heavily influence production decisions in banana growing regions. Changes in consumer preferences, trade policies, or economic conditions in major importing countries can have immediate impacts on plantation operations thousands of miles away. This global connectivity creates opportunities for rapid growth, but also exposes producers to external shocks beyond their control. The environmental impact of large-scale banana production has become an increasingly important consideration. Monoculture plantations can be vulnerable to pest outbreaks and diseases, requiring intensive pesticide use. Water consumption for irrigation and processing can strain local resources, while packaging and transportation contribute to the industry's carbon footprint. Labor considerations in banana production vary significantly by region and company. Large plantations typically offer more stable employment and better working conditions than small farms. But labor practices in the banana industry have been subject to scrutiny and reform efforts for decades. Worker safety, fair wages, and the right to organize remain important issues in many producing regions. The breeding and propagation of commercial bananas represents one of the most unusual aspects of modern fruit production. Unlike most crops, commercial bananas are not grown from seeds but are propagated through a process called tissue culture, which creates genetically identical plants from small tissue samples. The Cavendish variety that dominates global trade is essentially a single clone that has been reproduced millions of times. This uniformity ensures consistent size, flavor, and appearance. But it also means that every banana plant worldwide shares the same genetic vulnerabilities. This lack of genetic diversity is both the industry's greatest asset and its most significant risk. Tissue culture propagation begins in sophisticated laboratories where banana tissue samples are grown in sterile conditions on nutrient-rich media. The process requires precise control of temperature, humidity, and lighting to encourage healthy tissue development. A single tissue sample can potentially produce thousands of identical plants through successive generations of tissue culture. The laboratory phase of banana propagation typically takes 12 to 16 weeks, during which tissue samples develop into small plantlets with roots and leaves. These plantlets are then transferred to greenhouse facilities where they're gradually acclimatized to normal growing conditions before being transplanted to plantations. Quality control in tissue culture propagation is critical because any contamination or genetic variation can affect thousands of plants. Laboratories employ strict sterile techniques and conduct regular testing to ensure that plantlets are healthy and genetically uniform. This process requires skilled technicians and sophisticated equipment that represents a significant investment for banana companies. The selection of mother plants for tissue culture is crucial because the genetic characteristics of these plants will be reproduced in all subsequent generations. Mother plants are chosen based on their productivity, disease resistance, and fruit quality, and they're maintained in special facilities where they can be monitored and protected. Research and development in banana breeding focuses on developing new varieties that can resist diseases while maintaining the desirable characteristics of the Cavendish. This work involves both traditional breeding techniques and modern genetic methods, but progress is slow because banana reproduction is complex and time-consuming. The challenge of banana breeding is complicated by the crop's unusual genetics. Most commercial bananas are triploid, meaning they have 3 sets of chromosomes instead of the normal 2. This genetic structure makes them sterile and unable to reproduce through normal sexual reproduction, which is why tissue culture propagation is necessary. International collaboration in banana research involves institutions in both producing and consuming countries. Research centers in Ecuador, Costa Rica, and the Philippines work with universities and government agencies in the United States, Europe, and Australia to develop new varieties and improve production techniques. The timeline for developing new banana varieties can span decades because of the complex breeding process and the need for extensive testing. New varieties must be evaluated for productivity, disease resistance, shipping characteristics, and consumer acceptance before they can be considered for commercial production. Storage and distribution of tissue culture plantlets require specialized facilities and transportation systems. Plantlets must be kept in controlled conditions during shipping and handling to prevent damage or contamination. This requirement adds complexity and cost to the propagation process, but is essential for maintaining plant quality. The economic impact of tissue culture propagation extends beyond the immediate cost of plant production. The ability to rapidly produce large numbers of genetically uniform plants has enabled the expansion of banana production into new regions and the quick replacement of diseased plantations. The growing phase of banana production involves a complex interplay of agricultural science, environmental management, and labor coordination that continues year-round in the tropical regions where bananas thrive. Unlike seasonal crops, banana plants produce fruit continuously, requiring constant attention and management to maintain productivity and quality. Banana plants, technically large herbs rather than trees, grow from underground rhizomes that produce new shoots continuously. Each shoot develops into a pseudostem that can reach 15 to 20 feet in height before producing a single bunch of bananas. The entire cycle from planting to harvest takes 9 to 12 months. But because new shoots are constantly emerging, mature plantations produce harvestable fruit every week of the year. The establishment of new banana plantations requires careful site preparation and planning. Land must be cleared, drained if necessary, and prepared with proper spacing to accommodate the specific growth characteristics of banana plants. Modern plantations use precise spacing patterns, typically 6 to 8 feet between plants, calculated to maximize production while allowing for mechanized cultivation and harvesting. Irrigation systems in banana plantations are sophisticated networks of pipes, sprinklers, and drip systems designed to deliver water precisely when and where it's needed. Banana plants require large amounts of water, typically 1,200 to 1,500 millimeters annually. But they're also susceptible to waterlogging, making proper drainage equally important. Nutrition management in banana production involves regular applications of fertilizers tailored to the specific needs of the plants and soil conditions. Banana plants are heavy feeders that require significant amounts of nitrogen, phosphorus, and potassium, along with secondary nutrients like calcium and magnesium. Modern plantations use soil testing and plant tissue analysis to optimize fertilizer programs. The support systems used in banana plantations are essential for preventing damage from wind and the weight of developing fruit bunches. Props, typically made of bamboo or other materials, are placed under developing bunches to support their weight and prevent the plants from toppling over. This propping system requires constant maintenance and adjustment as plants grow and fruit develops. Pest management in banana plantations involves monitoring for insects, nematodes, and other pests that can damage plants or reduce fruit quality. Common pests include banana weevils, thrips, and various caterpillars that can cause significant economic losses if not properly managed. Integrated pest management programs combine biological controls, cultural practices, and targeted pesticide applications. Disease management represents one of the most critical aspects of banana production. Diseases like black sigatoka, a fungal infection that affects leaves, and Panama disease, which attacks the plant's vascular system, can devastate entire plantations if not properly controlled. Disease management programs involve regular monitoring, resistant varieties where available, and fungicide applications. The pruning and maintenance of banana plants requires skilled workers who understand the growth patterns and needs of the plants. Excess shoots must be removed to prevent overcrowding. Leaves must be trimmed to maintain plant health. And developing fruit bunches must be managed to ensure proper development. Weather monitoring and protection systems help plantation managers respond to changing conditions that could affect plant health and fruit quality. Extreme weather events like hurricanes, droughts, or excessive rainfall can have devastating impacts on banana production, requiring emergency response plans and protective measures. The harvesting cycle in banana plantations is carefully orchestrated to ensure that fruit is cut at the optimal stage of maturity. Bananas are harvested green and allowed to ripen during transportation and storage. So timing is critical to ensure that fruit reaches markets at the proper stage of ripeness. Record-keeping and traceability systems track every aspect of plant development and fruit production. This information is essential for quality control, regulatory compliance, and continuous improvement of production practices. Modern plantations use computerized systems to track everything from planting dates to harvest yields. The environmental management of banana plantations involves balancing productive agriculture with ecological sustainability. This includes managing water resources, protecting soil health, minimizing chemical inputs, and maintaining biodiversity in and around plantation areas. The pre-harvest phase of banana production involves a series of critical activities that determine the final quality and market value of the fruit. This period, typically the final 10 to 14 days before harvest, requires intensive management and precise timing to ensure that bananas reach markets in optimal condition. Bunch management during the pre-harvest period involves protecting developing fruit from environmental damage and pests. Plastic bags or covers are placed over developing bunches to protect them from insects, birds, and weather damage. These covers also help create optimal growing conditions by maintaining humidity and temperature around the developing fruit. The identification and marking of harvest-ready bunches requires skilled workers who can accurately assess fruit maturity. Bananas must be harvested at precisely the right stage of development, typically when they're still green but have reached full size and proper shape. Harvesting too early results in fruit that won't ripen properly, while harvesting too late can lead to overripe fruit that won't survive transportation. Quality assessment during the pre-harvest period involves inspecting fruit for defects, diseases, or pest damage that might affect marketability. This assessment helps determine which fruit is suitable for export markets versus domestic consumption or processing applications. Export quality fruit must meet strict standards for size, shape, color, and freedom from defects. Transportation preparation involves ensuring that harvest crews, equipment, and transportation systems are ready for the intensive activity of harvest operations. Banana harvesting requires coordination between cutting crews, packing stations, and transportation to processing facilities, all of which must be synchronized to maintain fruit quality. The timing of harvest operations is influenced by market demands, shipping schedules, and weather conditions. Plantation managers must balance the optimal maturity of fruit with the logistics of getting it to markets on time. This complex scheduling requires constant communication between plantations, processing facilities, and shipping companies. Worker safety preparations are essential during the pre-harvest period because banana harvesting involves working with sharp tools at heights and handling heavy bunches of fruit. Safety equipment, training programs, and emergency procedures must be in place to protect workers during harvest operations. Environmental monitoring during the pre-harvest period includes tracking weather conditions that might affect harvest operations or fruit quality. Rain, extreme temperatures, or high winds can delay harvest operations or damage fruit quality, requiring contingency plans and flexible scheduling. The documentation and traceability systems used during pre-harvest operations ensure that all fruit can be tracked from plantation to consumer. This tracking is essential for food safety, quality control, and regulatory compliance, particularly for fruit destined for export markets. Equipment maintenance and preparation involve ensuring that all harvest tools, transportation vehicles, and processing equipment are in good working condition. Banana harvest operations are intensive and time-sensitive, making equipment reliability crucial for maintaining operational efficiency. Market communication during the pre-harvest period involves coordinating with buyers, shippers, and distributors to ensure that harvest timing aligns with market demands and transportation schedules. This communication is essential for maintaining the complex logistics that move bananas from plantations to consumers. The coordination of harvest logistics requires detailed planning and communication between all participants in the supply chain. Harvest crews, packing stations, transportation companies, and processing facilities must work together seamlessly to maintain fruit quality and meet delivery schedules. Temperature management begins during the pre-harvest period with measures to protect fruit from excessive heat or temperature fluctuations that could affect quality. This includes harvest timing to avoid the hottest parts of the day and rapid movement of harvested fruit to temperature-controlled environments. The primary processing of bananas begins immediately after harvest and represents a critical transition point where field-fresh fruit is transformed into a globally traded commodity. This process involves a series of precisely choreographed steps that must be completed quickly and efficiently to maintain fruit quality and meet the demanding schedules of international shipping. The harvesting process itself is a skilled operation that requires experienced workers who can quickly and safely cut mature bunches from plants that may be 15 to 20 feet tall. Harvesters use sharp machetes to cut bunches, which can weigh 60 to 80 pounds, and must carefully lower them to prevent bruising or damage. The cut bunches are immediately placed on cushioned carts or conveyor systems for transport to processing facilities. Initial handling of harvested bunches involves careful inspection and sorting to remove any damaged or defective fruit. This inspection is crucial because damaged fruit can spread diseases or quality problems throughout entire shipments. Workers trained in quality assessment examine each bunch for signs of disease, pest damage, or physical defects that might affect marketability. The washing process removes field dirt, pesticide residues, and latex that naturally exudes from cut stems. Bananas are immersed in large tanks of treated water that may contain fungicides or other treatments to prevent disease development during shipping. This washing process must be gentle enough to avoid damaging the fruit while thorough enough to ensure cleanliness and safety. Bunch breaking involves separating individual bananas from the main stem and sorting them into uniform sizes and grades. This process requires skilled workers who can quickly assess fruit quality and size while handling bananas gently to prevent bruising. The sorting process determines which fruit will be packed for export versus domestic markets or processing applications. The grading and sizing of bananas follows strict international standards that specify acceptable ranges for length, diameter, and curvature. Export quality bananas must meet precise specifications for size, uniformity, color, and freedom from defects. Electronic sizing equipment may be used to ensure consistent grading, but much of the process still relies on skilled human judgment. Quality control during primary processing involves continuous monitoring of fruit condition, processing efficiency, and adherence to food safety standards. Quality control personnel sample fruit throughout the processing line to ensure that standards are maintained and that any problems are quickly identified and corrected. The treatment of bananas with fungicides and other protective compounds helps prevent disease development during the long journey from plantation to consumer. These treatments are applied in controlled environments using precise application methods to ensure even coverage while minimizing chemical use. Packaging of processed bananas involves placing sorted fruit into specialized boxes designed to protect bananas during shipping while allowing for proper ventilation and ripening. The packaging process must be completed quickly to maintain fruit quality and must follow strict procedures to ensure proper weight, count, and labeling. The yield calculations from primary processing help determine the economic efficiency of operations and provide feedback for improving cultural practices. Processing yields are affected by factors like fruit quality, handling procedures, and market standards, and this information is used to optimize plantation management practices. Labor management during primary processing involves coordinating large numbers of workers in fast-paced, time-sensitive operations. Processing facilities may employ hundreds of workers during peak harvest periods, requiring sophisticated scheduling, training, and safety programs to ensure efficient operations. The integration of processing facilities with plantation operations requires careful coordination to ensure that harvest timing aligns with processing capacity. Processing facilities must be able to handle variable volumes of fruit while maintaining quality standards and meeting shipping schedules. Environmental management in processing facilities involves handling large volumes of organic waste, managing water use and wastewater treatment, and controlling emissions from processing operations. The environmental impact of processing operations is increasingly important as the industry faces pressure to improve sustainability. The economics of primary processing involve balancing processing costs with fruit quality and market value. Processing operations represent a significant cost component in banana production, but they're essential for maintaining the quality standards required for international trade. Secondary processing in the banana industry encompasses a diverse range of value-added activities that transform fresh bananas into products with extended shelf life, different applications, and often higher profit margins. While the majority of bananas are sold fresh, secondary processing plays an important role in utilizing fruit that doesn't meet fresh market standards and in creating products for specialized markets. Banana chips production represents one of the most common forms of secondary processing, converting fresh bananas into shelf-stable snack foods that can be stored and transported without refrigeration. The process begins with selecting appropriate bananas, typically those that are fully mature but still firm enough to slice cleanly. The bananas are peeled, sliced to uniform thickness, and then either fried in oil or dehydrated to remove moisture. The dehydration process for banana chips requires precise control of temperature and airflow to ensure even moisture removal while preserving flavor and nutritional content. Industrial dehydrators use carefully controlled heating and ventilation systems to gradually remove moisture over several hours, resulting in chips with extended shelf life and concentrated banana flavor. Banana flour production utilizes unripe green bananas that are peeled, sliced, and dried before being ground into a fine powder. This flour is naturally gluten-free and high in resistant starch, making it popular among health-conscious consumers and those with dietary restrictions. The production process requires careful control of moisture content and particle size to ensure consistent quality. Frozen banana products include everything from individually quick frozen banana slices used in food service to pureed banana used in ice cream and smoothie production. The freezing process must be carefully controlled to prevent ice crystal formation that could damage cell structure and affect texture when the product is thawed. Banana juice and nectar production involves extracting liquid from ripe bananas and processing it into shelf-stable beverages. This process typically involves pulping, pasteurization, and packaging in sterile containers. The viscous nature of banana juice requires specialized equipment and processing techniques different from those used for other fruit juices. The production of banana-based baby foods requires strict quality control and specialized processing equipment to ensure safety and nutritional adequacy. Baby food production involves cooking, pureeing, and packaging bananas in small containers with extended shelf life, often combined with other fruits or ingredients. Banana leather or fruit roll-ups are produced by pureeing ripe bananas and then dehydrating the puree into flexible sheets. This process requires careful control of temperature and humidity to achieve the proper texture and moisture content while preventing spoilage or quality degradation. Industrial banana processing for use in bakery products, ice cream, and other food applications involves producing standardized banana purees, concentrates, and flavorings that meet the specific requirements of food manufacturers. This processing requires sophisticated quality control systems and the ability to produce consistent products year-round. The utilization of banana byproducts represents an increasingly important aspect of secondary processing. Banana peels, which represent about 30% of the fruit's weight, can be processed into animal feed, fertilizer, or even biodegradable packaging materials. This utilization of byproducts improves the overall economics of banana processing while reducing waste. Organic banana processing requires separate facilities and procedures to maintain organic certification throughout the processing chain. Organic processors must use approved ingredients and processing aids while maintaining strict documentation and traceability systems to ensure compliance with organic standards. The equipment used in banana secondary processing must be designed to handle the unique characteristics of banana products, including their tendency to brown when exposed to air and their varying moisture content. Specialized equipment for peeling, slicing, dehydrating, and packaging is required to maintain product quality and processing efficiency. Quality control in secondary processing involves testing for moisture content, microbiological safety, and sensory characteristics. These tests ensure that processed products meet specifications for shelf life, safety, and consumer acceptability while maintaining the nutritional and flavor characteristics that consumers expect. The economics of secondary processing must account for the additional costs of processing, packaging, and marketing while capturing the value premium that processed products can command in the marketplace. Successful secondary processing operations require understanding both the technical aspects of processing and the market dynamics that determine product profitability. The distribution and marketing of banana products represent the final and perhaps most complex stage of the banana supply chain, involving a sophisticated network of transportation, storage, and retail systems that must coordinate across multiple countries and time zones to deliver fresh bananas to consumers worldwide. The cold chain logistics that move bananas from tropical plantations to temperate markets represent one of the most sophisticated temperature-controlled distribution systems in the food industry. This system begins at processing facilities where bananas are loaded into refrigerated containers, called reefers, that maintain precise temperatures throughout the journey to destination markets. Refrigerated shipping vessels, purpose-built for banana transport, can carry thousands of containers while maintaining different temperature zones for various stages of fruit maturity. These ships are equipped with sophisticated climate control systems that can adjust temperature, humidity, and air circulation to optimize fruit condition during voyages that may last 2 to 3 weeks. The port handling of banana shipments requires specialized facilities and equipment designed to maintain cold chain integrity while efficiently transferring containers from ships to land-based transportation. Major banana importing ports like Miami, Houston, and Long Beach have dedicated banana terminals with temperature-controlled storage areas and rapid container handling capabilities. Ripening facilities represent a crucial link in the banana distribution chain, where green bananas are transformed into the yellow fruit that consumers expect. These facilities use controlled atmosphere chambers where bananas are exposed to ethylene gas, which triggers the ripening process, while temperature and humidity are carefully managed to ensure uniform ripening. The ripening process typically takes 4 to 6 days and requires skilled technicians who can monitor fruit condition and adjust environmental controls to achieve the desired ripeness level. Different customers may require different ripeness levels, from green bananas for wholesale markets to fully yellow fruit for immediate retail sale. Distribution centers that handle banana products must be equipped with temperature-controlled storage areas and rapid throughput capabilities to maintain fruit quality while meeting the demands of retail customers. These facilities often operate 24 hours a day to accommodate the continuous flow of banana shipments and the need for rapid delivery to retail stores. The retail distribution of bananas involves sophisticated inventory management systems that track fruit condition, sales velocity, and optimal display techniques to maximize product quality and minimize waste. Retail stores must balance maintaining adequate inventory with the limited shelf life of ripe bananas. Transportation from distribution centers to retail stores requires refrigerated trucks and careful handling to prevent damage to ripe fruit. The timing of these deliveries must be coordinated with store receiving schedules and sales patterns to ensure that bananas reach consumers at optimal ripeness. The marketing of banana products involves promoting not just individual brands but the entire category of bananas as a healthy, convenient food option. Industry marketing campaigns focus on nutritional benefits, convenience, and versatility while addressing consumer concerns about sustainability and fair trade practices. Brand differentiation in the banana market is challenging because the product is largely standardized, but companies compete on factors like quality consistency, sustainability practices, and value-added services to retailers. Premium positioning often focuses on organic certification, fair trade practices, or superior logistics capabilities. The export market dynamics for bananas involve complex negotiations between producing countries, multinational corporations, and importing nations. Trade agreements, tariff structures, and quality standards all influence the flow of bananas in international markets and affect the economics of banana production and distribution. Consumer education about banana storage, ripening, and use helps maintain demand and reduce waste at the retail level. This education involves providing information about optimal storage conditions, ripeness indicators, and creative uses for bananas at different stages of ripeness. The pricing of banana products reflects the complex interplay of production costs, transportation expenses, market competition, and retail margins. Despite the sophisticated logistics involved in banana distribution, competitive pressures have kept retail prices relatively stable, requiring constant efficiency improvements throughout the supply chain. Quality assurance throughout the distribution chain involves continuous monitoring of fruit condition, temperature control, and handling procedures. This monitoring helps identify potential problems before they affect product quality and provides feedback for improving distribution practices. The environmental impact of banana distribution includes the energy consumption of refrigerated transportation, packaging materials, and the carbon footprint of global shipping. Industry efforts to reduce environmental impact focus on improving logistics efficiency, reducing packaging waste, and optimizing transportation routes. The complexity of banana distribution creates both opportunities and vulnerabilities. While the sophisticated logistics enable year-round availability of affordable bananas, disruptions to any part of the system can have rapid impacts on fruit quality and availability. Natural disasters, port strikes, or transportation problems can quickly affect banana supplies in markets thousands of miles away. The banana industry's remarkable achievement in creating a global supply chain that delivers consistent, affordable fruit year-round represents one of the most sophisticated examples of modern agricultural logistics. Yet this same system's dependence on a single variety and its vulnerability to disease, climate change, and supply chain disruptions highlight the inherent risks in our globalized food system. The banana story reveals both the possibilities and the perils of modern agriculture. The industry has succeeded in making a tropical fruit as available and affordable as any local produce. But this success comes with environmental costs, social challenges, and genetic vulnerabilities that threaten the entire system. As we've seen throughout this journey from plantation to plate, the banana industry represents the ultimate expression of agricultural industrialization and global trade. Every aspect of production, processing, and distribution has been optimized for efficiency and scale, creating a system that can feed millions of people while generating billions in economic value. Yet the banana industry also illustrates the limitations of this approach. The genetic uniformity that enables consistent quality and efficient processing also creates catastrophic risks. The environmental impacts of monoculture production and global transportation are becoming increasingly difficult to ignore. Labor conditions and economic inequalities in producing regions remain persistent challenges. The future of banana production will likely require fundamental changes in how the industry operates. New varieties with greater disease resistance and genetic diversity are urgently needed. More sustainable production practices and supply chain efficiencies will be essential. The development of regional production systems might reduce dependence on global shipping, while improving freshness and reducing environmental impact. The banana industry's experience with these challenges offers important lessons for other agricultural sectors. The benefits of specialization and global trade are substantial, but so are the risks. Building resilience into agricultural systems requires balancing efficiency with diversity, global reach with local adaptation, and economic optimization with environmental sustainability. As we turn to our final chapter in this exploration of modern agriculture, we'll examine another fruit that has experienced explosive global demand, but has taken a very different path to market success. While bananas represent the pinnacle of agricultural standardization and global logistics, avocados tell a story of premium positioning, supply chain innovation, and the challenges of scaling up production to meet rapidly growing consumer demand. The avocado industry's transformation from a niche crop to a global phenomenon reveals different strategies for building international markets and managing agricultural supply chains. Where bananas succeeded through uniformity and scale, avocados have thrived through premium positioning and supply chain innovation that can deliver peak quality fruit to demanding consumers worldwide.